This is the first oscillator I made with a third overtone 10 MHz crystal. Here is what it looks like on the inside. Here is the phase noise in the most interesting frequency range from 0.5 Hz to 1.5 Hz. I have plotted it on a piece of paper because I want to compare with the measurements using the interferometer. It was number 4 in my series of 10 MHz low noise oscillators. 4th design, nerds67 up to nerds74. And you can see what it was about. At the time when I did this, the only oscillators I had as references used standard computer-grade 10 MHz fundamental crystals. So they were fairly noisy, and I could not measure close-range noise at the time. So the design was for a very low noise at large frequency separations. Now I need this oscillator. I'm using it as the local oscillator of my 2-channel direct conversion receiver. And I needed to measure very low noise at very close offsets from the carrier. So I need a very low phase noise at separations about 1 Hz and below. So I need to redesign this oscillator. It is about 6 decibels more noisy than it should be at 1 Hz. Here is the close range phase noise that I just measured from 0.1 Hz here up to 4 Hz here. And it forms a very good straight line, although here it is off by about 2 decibels. Here is the frequency response. Q is 1.26 million, so it's pretty high. The phase angle is off by, what does it say? About 7 degrees. I don't think this can have any effect on the sideband noise. I have placed marker number 1 on the place where the phase angle is 0, and then I look at the amplitude, and the error I see is very small. The distance from the peak, if I move the marker, you can see it's 0.09, and on the peak it puts 0. So it's less than 1/10 of a dB from the maximum. When the unit runs as an oscillator, the level I see is 3 volts peak to peak. That's 13 dBm, about 20 milliwatts. Now I'm running the unit in the interferometer at a very similar signal level at the output, and the input is on the sources of the many JFETs that are connected to the crystal filter. The carrier suppression now is 40 decibels, and I can tune the phase angle, and you can see that this is the minimum. So I know that the phase of the carrier is correct to detect AM and phase noise properly. Here is the close range phase noise with the interferometer at 40 decibel carrier suppression. The carrier I use into the interferometer is very close to the local oscillators in the 2-channel receiver. That means that the frequency of the audio from here to here is only about 7.5 Hz. That means that I have some error at 7.5 Hz here, so this region is not useful. And also twice that frequency, 15 Hz, has an artifact. And then here at about 40 Hertz there is a funny peak. This is because the crystal is also connected, and it is about 50 ohms and gives a source resistor for the FET, and that creates noise. So the true curve goes like that, and I have to skip this region, but I can trust the result way here, where the impedance of the crystal is very high. I have disconnected the crystal, and now there is no peak at about 40 Hertz as there was before. The lower trace here, it goes like this, is the phase noise, and the white trace here is amplitude noise. And it's clear that the region around 7.5 Hertz, that is the separation between the local oscillators and the signal generator I'm using in the interferometer. That's the 2-crystal oscillator I have. The 7.5 Hertz is too close. There is still an influence from the characteristics of the sound card. The sound card has a high pass filter. It is AC coupled, and we can see here this characteristic thing. Probably there is almost only amplitude noise, but part of it comes as phase noise with the maximum here and here because of the phase shift due to the high pass filter with a characteristic frequency of maybe 1 Hertz or so. And we can see, of course, the notch at the center. DC is completely blocked. Maybe the correlation that can be seen here is an artifact of some kind. I will try to find out whether calibrating Linrad properly will change that. Here is the internals of my sound card. It's a modified prototype for the UADC4. The input is just a capacitor, 2.2 microfarads, and then into the differential amplifier. And then there is a second equally big capacitor to decouple the plus input of the same differential amplifier. And then for 4 channels. I have added 2 4700 microfarad capacitors in parallel to each coupling capacitor, which was previously only 2200 microfarads. This means that I have modified the time constant from 0.86 seconds to 4.5 seconds. That's a factor of 5. I found this RC filter calculator on the internet, and this is my original sound card. And then I can see the phase plot. The carrier at 7 Hertz, 7.5, it's about here. It is twisted something like 15 degrees away from where the noise sidebands are when they are far away from the center. So that could explain the correlation I saw at large frequency separations. With the increased capacitor, 11,000 microfarads, I get this curve, and I then see at 7 Hertz up here, the phase shift is very small and very similar to what I should expect at much higher frequencies. This did not make much of a difference. I didn't save the previous result, but I think this is fairly similar. A little smaller, but not much. And we still have this artifact. This is the notch. So that is quite okay. The increase in phase noise is an artifact because the phase of the modulation is shifted here, where the high-pass filter cuts. It seems I have to move the frequency for the oscillator that I'm using in the interferometer. I didn't like that because it involves tuning the two-crystal oscillator. Now the signal is 22 Hz above the local oscillator, so the offset is about 3 times larger. And I think this will remove difficulties from these artifacts from the DC frequency. Already after 10 minutes I can see that this looks really odd. The level at 50 Hz was before about minus 170. Now it is minus 164. That's a 6 dB difference. And I can see here the correlation between AM modulation and phase modulation is much higher. Maybe I have made an error in the interferometer. I have to check that. So I tuned the phase knob to see if I really have a minimum here. Yes. So something else is bad. Here is what I see with 50 decibels of carrier suppression. The structure here is very strong. That's the noise at zero frequency. And here is amplitude noise and phase noise at the same time. And it looks really odd up here. Something is common between the two modulation forms. The signal to noise ratio of the noise measurement is very good now with 50 dB carrier suppression. From the amplitude noise here down to the noise in the correlation measurement is this distance from here to here. And that is, what is it, 125 minus 108. So it's more than 15 decibels. I have changed the interferometer, so there is now only 30 decibels of carrier suppression. And as you can see, the noise background has not changed much. It's a small difference. Very hard to see. It's much easier to see in the baseband waterfall, where you can see that there is more noise close to the carrier. Anyway, the previous measurement was like this, and I have changed the scale by 20 decibels. There is a small discrepancy if you see the red track here, and now it is 1 decibel lower. Here is what I see with 30 decibels of carrier suppression, and I set the carrier at 120 dB. And here is the result I had with 50 decibels of carrier suppression. And with the screen like this I don't see, but the carrier was set at 100 dB. So those 20 dB are compensated for, and the curve looks very similar, or more or less identical. I can put a mark, for example, here. And this is the new result. And here is the old. And the curve here, that might differ. Yes, because this is the sound card 1/f noise, while this is the correlation spectrum. So this changes, but this does not. I will evaluate this, but first have a look at the amplitude noise. And here is the amplitude noise. This artifact is not very great. I don't remember exactly how it was before, I didn't save it. But more interesting is this, where I have the correlation. It seems this is real. There is a correlation between AM noise and phase noise. Although the fact that it differs on the two sides is suspicious. So I don't really know, but if there is a correlation, it is just an indication that both forms of noise modulation have a common origin, and that is not unlikely at all. With 30 decibels of carrier cancellation in the interferometer, I get these points, the blue dots here, and here they coincide perfectly with the previous measurement. But then here are new points, and there is a discrepancy that I can't explain. Anyway, the curve shape, it's not 1/f kind. The amplitude noise is these quadratic boxes with a cross in it. And the accuracy is very good statistically. The expected 1/f slope is these red lines. And then here is the artifacts due to the DC frequency. I don't know what kind of conclusion to draw from this. Maybe I will find something when looking further at this. I'm now looking at the feedback output of the unit, and this is really surprising. I have now 30 decibels of carrier attenuation, but you can see here this looks far more noisy. And when I compare to the saved screen, looks like this. From here to here is 7 decibels or so. And I can see, of course, here something is very wrong. I have no idea, but it's not many components that are involved, so I will first make a schematic diagram of this section and then try where is the problem. Here is the output amplifier. I have measured the output signal at this point, and that was a little noisy but not so bad. Now I'm looking at the feedback output, that's here, and it is very noisy. But both signals come from the drains of these 6 parallel transistors, and the noisy signal goes this way. This is a delay line with 7 links to provide the appropriate phase shift. So something is bad in here, or in there. When looking carefully, I can see possibly there is a poor soldering at the ground point of the 2 diodes here. I have twisted the legs of the diodes and soldered, and there is a little bit that isn't soldered where the wires are close to each other and making perhaps a bad contact. So I will heat it up and put some tin on it. This seems to have made some difference here. This was before I heated the diodes, and this is after. Here is when I put the camera in its holder, so I have made vibrations on the table. But when I compare with the saved result here, it is still not good. If I look from, let's say, here to here, it is 1, 2, 3, 4, 5. It is 6 decibels now. I think it was 7 before. So this is a very small improvement. If it really is an improvement, I don't know for sure. Now I have disconnected the delay line, 7 links of LC that was intended to set the proper phase angle. There are still obvious problems, as you can see up here. Some noise bursts from I don't know where, but when I compare with the saved spectrum, this one, I can check here at I think 100 Hertz. The difference is now only 1, 2, 3 decibels. So this is better, but something is still bad. Now with the amplitude limiter, the amplitude noise, the white trace is lower than the yellow trace here by about 3 decibels. And the correlation between AM noise and phase noise is high. So maybe limiting the amplitude noise causes phase noise. Amplitude modulation may cause phase modulation. I have seen that before and made a video. To find it, you can go to my home page and then click Linrad here, and then the first link here. To see a list of all the videos. There you can find this video, nerds84, correlation spectra number 8. It is about this oscillator, which suffers from phase modulation as well as amplitude modulation. By introducing a limiter with diodes and some filters around that limiter, it's possible to convert part of the amplitude noise to phase noise and make that cancel the phase noise that comes from the unit when nothing is added to it. Knowing that filtering makes a difference, I have moved the amplitude limiter from here to here, and I also doubled the number of diodes to get a sharper clipping function. I'm still looking at the feedback output, but now with the clipper on the other side on the delay line. And the old result I had was this. This is from the main output. And the feedback output was much more noisy before. But now it is significantly less noisy. So I will convert this back to an oscillator again to see what happens. This does not look good at all. At 0.1 Hertz here, it is about 73.5 dB. And 0.2 Hertz minus 88. And it was better before I moved the place where the amplitude limiting is done. And the better feedback signal has caused a degraded output. I have lost at 0.15 Hertz a bit more than 10 decibels in increased phase noise. But a little bit further away from the carrier at 1 Hertz, that's still pretty close, the difference is only 2 decibels. And at 5 Hertz there is no difference. So moving the diodes was a bad idea, although it seemed so reasonable and the feedback signal was so much better. I think it's time to give up this design. I will do something based on the experience on previous designs that I did after I did this, which was the first one I made with these crystals. This time I want very low noise close to the carrier, but the flat noise floor is of minor concern. It will be low enough to be well below the noise of the sound card, because the purpose of this unit is to use as an oscillator in my 2-channel receiver. So here I have two BF240 that will run in parallel. As you can see, they are mounted on a copper surface, each one, and with very low inductance capacitors to ground and between those surfaces. That is because paralleling this kind of transistors is difficult because they easily form oscillators in the UHF range. There will be push-pull resonators and parallel resonators with low losses at very high frequencies, typically 500 to 1000 megahertz. So that's why I try to keep resonances above 1.5 gigahertz, where they won't oscillate. A low inductance wire, a copper strip, between the collectors when connecting in parallel may reduce the risk of creating oscillators in this parallel high-speed transistor configuration. I have changed the input stage now from using many JFETs to using two bipolars, BF240. The 0.1 microfarad capacitor has a series resonance at 10 megahertz. So this resistance, the losses of it, are invisible to the transistor. There are two transistors, so the 1/F noise from them is not correlated. That might reduce noise just a little. And then I have a transformer, 10 to 1 in voltage. And this goes into the next stage, which has an input impedance in the order of 50 ohms. And now I can turn it into an oscillator just to see what happens. With the other stage unchanges, and the diodes are still clipping at the output of the delay line. And here is what it looks like. I will tidy it up if it looks promising. The sideband noise is a little bit higher than before. This is phase noise. The amplitude noise is much lower than before, and the correlation between amplitude and phase noise is small here, where the phase noise is so strong. Means it has a different origin than the amplitude noise. Although at wider separations it seems they start to get a common origin. The phase noise now is the blue dots here, this line. So I have degraded a bit further, but the straight line goes to lower frequencies as compared to this bent curve I had with the previous experiment with the JFETs. I think the reason may be that the load at this point is very high, in the order of 5 kilo ohms, because this is 10 times in amplitude, 100 times in impedance, from 50 ohms up to 5 kilo ohms. And I don't know exactly what it is, but high in any way. So I will put the resistor from here to here and remove a resistor I have on the feedback output to make a lower impedance for the bipolars, and also of course lose some of the noise floor at wide separations, but at the moment I just want to look close to the carrier. When I remove the resistor in series with the output connector of the feedback, then the gain increases by a little more than 6 decibels. A resistor of 2.7 kilo ohms here brings back the same gain as before. As it turns out, this does not affect the noise, it's the same, these blue marks that I had before. I have removed the 2.7 kilo ohm resistor from here to ground, but I have not put back the attenuator on the output to the feedback, and this caused the signal level to go up by 6 decibels. The amplifier chain is heavily saturated now, and the waveform is very ugly, but if I press the bandwidth limit button, it looks nice again. But it has a lot of high overtones, of course. We'll see what that makes to the phase noise.
Now, when the output level is saturated at a level 6 decibels higher, the phase noise is 6 decibels lower. So there is obviously a problem in the second or maybe third amplifier stage. I will replace them. I have moved the limiting diodes to the input of the delay line. The level is now 2 decibels lower. There is some small clipping up here, but not much. And the waveform looks more normal. Bandwidth limiting, you see, it is a little weaker because of the clipping.
Now the phase noise is high again. At 0.2 Hz, it is about -87. So moving the clipping diodes has the same effect as before. I see this as a current amplifier. And I made some measurements on it. Everything is peak to peak. With a 100 ohm resistor here and 250 millivolts here. I have 2.46 milliamps through the resistor, and there is only 4.2 millivolts here at the emitters. And I have to measure exactly at the emitters, because if I measure on the wire of this resistor, I get a much higher voltage because of the inductance of wires. This means that the input impedance is only 1.7 ohms. So it is a high impedance source here, 100 ohms, and the amplification is on the current. The output with a series capacitor of about 500 pf, and I have to tune it, I can get a minimum in the voltage at this output of the transistors. If I don't tune, there will be saturation in this point with a very high voltage. And it's about 500 pf to tune. In this point, the voltage is 530 millivolts, but the output is 52 millivolts only. But it's across 1 ohm, so it means 52 milliamps. Current gain is thus 21 times, and that's far more than the 8 times one would expect from the turns ratio of the transformer. So it has to do with something with the what is it called? The leak inductance between the windings that I'm tuning with this capacitor, I think. Anyway, when I send 5 dBm into the crystal with the normal arrangement here, I have 35 milliamps peak to peak here through the 1 ohm resistor. This means if I make an identical amplifier for the next stage, it will have 52 milliamps input. And these transistors have 20 milliamps each. That means I have 40 milliamps. Means current will go from 57 down to 22 milliamps. That is reasonable. It shouldn't be too non-linear. If I load it with 200 ohms, that gives me 7 volts, or 3.5 volts across 50 ohms, and that's 13 dBm. So that would be enough to create an oscillator and to send about the same, well, more than that, into the next stage, which would be an isolating buffer stage. So I will go in this direction to see if I'm thinking in a way that agrees with what I will expect when I try to do this.
Here is the output impedance. The impedance at the point where I have the 1 ohm resistor. And I think this is going to be fine, because I want to feed this type of amplifier from a current source. And this has a high impedance, so it is a current source.
Here is the schematic diagram I have arrived at. This amplifier you have seen before, and here is an identical one, and the output is a toroid with a transformation 3 times, and there is a tuning capacitor here, and I'm measuring now the response from input to the feedback output, but I have disconnected this capacitor by breaking here. Here is the frequency response. I am tuning now the capacitor at the output of the second stage. And you can see it gives a maximum at 10 megahertz. That's where the cursors are. So proper tuning is about like this. But still, the signal is much stronger here, which is about, is it 17 megahertz or something? The peak is at 17 megahertz, 16.7 or so, but the desired one is at 10 megahertz, and we don't see the resonances of the crystals. They are far too sharp to be seen with this wide frequency span. And there is a peak also here at 5 megahertz. I have reconnected this capacitor and tuned it to balance the parallel capacitance of the crystal. The level now is generally about 30 decibels lower or more. At 10 megahertz I can see the interesting resonance here. We have the fundamental here and spurious resonances, a lot of them, and the fifth overtone, I guess, and I don't know what that is. But these resonances are strong. There is a risk that oscillations could happen here, or maybe here, or maybe elsewhere, depending on the phase shift. Here is the fundamental at 3.367 megahertz, and the loss is 10 decibels, and the Q 756,000. Here is the second harmonic, a lot of resonances. I picked the strongest one at 6.3 megahertz and zoom in on it. Well, the level is not so high, minus 18 decibels, and Q is small, only 134,000. For one of the peaks, and I don't want to spend time to look at all the others, the second harmonic is probably very useless for an oscillator. Difficult to pick what resonance to use, and the Q is not particularly high. Here is the third overtone. Many resonances, and if I look with the marker, I find that this is the one at 10 megahertz, and then there is at 10.08, that's only 89 kilohertz up, and the other one is 99, and then there is a strong resonance at 10.2 megahertz, and then a couple of more ones. I will look at them with higher resolution. The Q is 1.309 million, and the frequency 10.000016 according to this network analyzer. And the loss, well, the gain is 5.3 decibels. Here is the next resonance, Q 1.346 million and center frequency 89 kilohertz above 10 megahertz, but the gain is below zero. It is minus 0.76 decibels. Here is the next one, Q 1.346 million and 99 kilohertz above 10 megahertz, and the loss is only 0.4 dB. Close to the resonance, the parallel capacitance has a component of vibrations in the quartz, so this curve is asymmetric, and I will change the capacitor that compensates for the crystal parallel capacitance. Now the filter curve is symmetric. What I had before was this, or rather here it is. So I don't think it matters at all, but this looks more nice. In order to get the correct phase angle on the peak, I have mistuned this capacitor slightly, with a very small influence on the amplitude of the peak. Noise performance is reasonable, 0.2 Hz, 100.5, 0.5 Hz here, about minus 114, and 1 Hz here, it is 123. Not too bad, the values come here. And compared to the NEL 1714A, which is pretty good. I have added a series resonator here at the output in order to set the phase angle to 0 at the peak of the resonance of this coil. This did not make much of a difference. I see now 98 instead of 100.5 at 0.2 Hz, but at half an Hz it's only 1 decibel, and at 1 Hz there is no difference, minus 123. So here again, this is what I have now. I have moved the clipping diodes to the other side of the output series resonator. And I don't know whether that matters or not. We will see. I have placed a 100 ohm resistor here. And this capacitor was in place in the previous experiment. I don't know whether it makes a difference or not. This resistor has reduced the amplitude of the oscillations by 1 decibel. The phase noise is a little lower at 0.2 Hz. 103 rather than 101. But further off from the carrier there is no difference, or at least a small difference. I have changed these diodes from ordinary silicon diodes 1N4148 to Schottky diodes BAT42. By doing so, I have reduced the output from the unit here by another 4 decibels. Now I see at 0.2 Hz minus 101. So it is less good than before. At 0.5 it's about 113.5 or so here. I have made a change in the opposite direction. Series connecting 4148 and BAT42. This increased the signal level by 5 decibels at the output, And this means I am back at the same level as I had without that resistor and with the two 4148 diodes. The difference is small, possibly in the right direction. I have 103, 114.5 and 123.5. So it's about half a dB, and I'm not sure it is significant. But it's much better than what I had when I started. So the arrangement around the diodes is important. In an attempt to get better control over the limiting, I have made a limiting stage with two bipolar transistors and various resistors to optimize to see what will be the lowest noise. I have modified the Linrad code. Now it gives me the average here over the region which is in green. This camera doesn't show it well, but when I move it you can see from here and to the end of the graph the borderline is green. Means I'm computing the average of all the decibel values over that region, and that comes here as first time minus 116.8, second time 115.8. And here is the next. And I can wait for a while, and this is an average of many data points, so it converges fairly rapidly. And I have set a fairly large bandwidth when doing this. So this way I can quickly get the result. Now, sitting in front of the screen, I may shake the table and then I get some interferences that I can see here. Now, I run into a difficult problem. The oscillator box is lying upside down now. I turn it very gently, like this. And of course I get transients now, because I'm vibrating things inside, but I wait for a while. I now clear the graph to collect new averages. This was the latest one. I insert some line feeds to see where the new results come. And now performance is degraded by 3 decibels. And I can see that also in the baseband graph. Here the white trace is much wider. And this is perfectly reproducible. And I have looked for something that can explain it, and I have not yet found any reason for this behavior. I find nothing inside the box that I think could possibly explain this behavior, so I have opened the thermostat and I will turn the crystal half a turn so it will come upside down as compared to before. Now I turned it half a turn so it is upside down. Performance is now still good, minus 115.5 for the average. And when I look here, it looks like this narrow trace, not like the wide that I had here. And I will turn the box again. And now it's no longer upside down. And now, when I turned it right again, the noise is much higher. The average is 112. Well, minus 112 for this range from here to here. And the baseband graph shows that clearly. But it also shows that the noise is increasing with time. This was when I turned it upside down. Turned it right again after having been upside down, and now it seems to widen. The unit is now running as an amplifier. I inject a weak signal into it, and I have added a low noise amplifier at the output. The weak signal -80 dBm is at the center of the crystal filter. As a result, I have a carrier here, not very strong, surrounded by a flat noise floor, perfectly flat. And then the evaluation of the phase noise looks like this. And I have been forced to set very slow processing to get the flat noise floor all the way down to 0.1 Hertz. Because I have seen that noise tends to increase rather rapidly at very low offsets. So this is the way I will evaluate, and at this site the average is 38.52 over this range from here up to here. And I will set it a little bit more carefully, a little bit above 0.1 Hertz when evaluating oscillator performance. I have increased the bandwidth of the baseband filter by a factor of 4. And as a result, the accuracy of the flat noise floor is good only up to this point. And that is 0.35 Hertz. And that is the region where I want to measure. So this is not permitted. I have to go back to a very narrow filter to extract the carrier used for demodulation. I have set a 4 times smaller transform size for the spectrum of the modulation. So it is now 2 to power 16, the same as I have in the baseband window. It says 16 here, which means that the 3 dB bandwidth is about, you can see here, that is 0.05 Hertz roughly. So that's the resolution I have here. This makes the process faster as compared to before. The scale here is 0.2 decibels per division, and the average of this curve is very reproducible. It's 37.74 now. And I can read, I have set the green region here, which you can see when I move the camera at this point. And that's where the flat region starts. So I think this is optimum settings to compute the sideband noise with various adjustments on the oscillator that I am trying to optimize. I have disconnected the pace lock loop between the 2 reference oscillators in my 2-channel receiver. And then I am listening to this box again, and set in the worst position where the noise is highest. And it's particularly high at the lowest frequency, 0.1 Hertz. So here I see the frequency stability, and to what extent there is a correlation between these 2 traces is very hard to say. This trace, which is not so stable, that's the Wenzel oscillator, and this is my own homemade one. I have connected the Wenzel oscillator to a better power supply, and it is more stable, but it is still not stable enough to be able to find some correlation between the traces by eye, just like this. But I think the convergency of the correlation measurements will be a little bit faster now. I may have forgotten to say that I have reduced the attenuation in front of the 2-channel receiver, so it is saturated, and that's why there are so many overtones. And what I have seen here with the oscillators is about 1/100th overtone. So 1 hertz from here to here is 1/100th of a hertz. I am running at the lowest possible capacitance now. There is still a 3 dB degradation when I turn the box right. It is of course also visible in the baseband waterfall. Here is upside down and here is why I turned the box. And one can see immediately that the noise is higher. Here I started measurement with the unit upside down, up to this point. Then I turned it with the connectors up, and noise has increased significantly. And the number here is 98. It was 105 or so when it was upside down. So the position sensitivity has become worse. Now the unit is upside down again, and the average noise is minus 106 decibels. That's below the carrier. Problem solved. The box, which is airtight, is not stiff enough. So when I turn it upside down, for some reason, the mechanical movement when the upside, this side of the box, is subjected to infrasound, the small movements change the frequency far more when the box is in this position as compared when it's upside down. Now this side is stiff. I put a lot of effort to that, and now there is no difference when I turn the box upside down. The improvement from this modification is about 1 decibel with the box upside down and 4 decibels in this configuration when the upside is up. I will now look at the effect on the phase noise of different settings on this capacitor, the main tuning capacitor that is parallel to the crystal, because this is essentially a ground point. So this is the high impedance point on the crystal. And how that setting, the noise from it, varies with the setting of the coupling capacitor. So I'm trying to optimize this circuit. I'm measuring the phase noise the way I just demonstrated, and I will have to wait for maybe 20 spectra to get a stable reading. I have the SDR-IP units running at the same time, and I use them to measure the signal level. So it is 23.78 now. And I read the frequency in the baseband window, means 92.02 Hertz, above 10 megahertz. Here are the results. I have loaded the feedback output with a resistor, that is a 50 ohm dummy load, or 2 50 ohm dummy loads in parallel. That is to get a lower amplitude of the oscillations. I have also tried a fairly large coupling capacitor and a smaller one. This is the angle that I measure on the capacitor. And then tuned different number of turns here, and I note the frequency and the signal level, and the interesting thing, that is the average sideband noise, the average phase noise, and this is negative in decibels. So starting with a big capacitor and no load, I get a very high signal level, 27 decibels, but the noise is not particularly good. And then when I increase the tuning capacitor, the sideband noise improves, because the impedance at the high impedance point goes down, so the coupling becomes smaller. And the signal level goes down from 27 down to 23 decibels. And then with a smaller capacitor, I get much better performance. And I'm starting from the maximum capacitance, so I'm going the other way. But so the improvement by reducing the capacitor at 20 turns on the tuning capacitor, that is very small. But when the capacitance here is minimum, the frequency is maximum, then the improvement is 3 decibels. I have plotted these results. Performance, that means average sideband noise, goes up to about minus 113 decibels. That's this group. And the signal level varies with no resistor and a big capacitor, no resistor and a smaller capacitor for the coupling, and then adding resistors with the small coupling capacitors. And the optimum to use is, of course, somewhere in this region. I have placed the oscillator inside a reasonably airtight box. And I have waited quite some time, 426 averages, and I see 111.97. I have opened the box and made no other change. The difference I can see in the baseband graph is significant. It's much wider here. And I can see in the average sideband noise, it is now 107. It was about 110 when I measured it previously. Maybe the infrasound level changes from one day to another. Anyway, this is a big problem because oscillators that have a common noise source and used in a 2-channel receiver for correlation measurement, since they are correlated, they will give a false reading with too high noise level. I think I have now found the reason why performance at 0.15 Hz here was about 3 decibels or 4 decibels worse than expected from the straight line. I think infrasound starts to have an effect here at 0.7 Hz and it's increasing. So this is problematic. I need airtight boxes or stiff boxes to place the oscillator in. I have sealed the box to make it airtight and then measured it upside down and upside up. And the result differs significantly, which it shouldn't do. So I placed the sealed box inside this larger airtight box. And the result is significantly different. The noise is lower, and I see after 195 averages 111.41. With 460 averages, the statistics has improved a bit. It says now 111.84. The lid of the wooden box is not particularly tight. I removed this tape that I have had around it and reset and collect data again. The lid of the box is obviously tight enough. Now with 423 averages, I see 111.98. And this is the box with this slit here, which is not very wide but 1 centimeter long. and not harmful. Here is how I sealed the box to make it airtight. These things are used to tighten windows in the wintertime. Maybe the problem is that this wall here is moving a little. It is very close to the main tuning capacitor here, and very small movements would change the tuning. I have replaced now 0.8 mm hard copper by 3 mm hard aluminium to see whether this lid was not stiff enough. The thicker lid made no difference, 110.66. The previous one, sealed upside up, was 110.62. So that's almost identical. I have made the box wall stiffer, close to the tuning capacitor. This has made a significant difference. Now I see 111.81 at 448 averages. That's enough to have a significant result. So I have the results with the tuning capacitor's 7 turns from minimum. This was the original, and it is the same settings here, but this is with the unit inside the box, the wooden box, and the difference from here to here is nearly 2 decibels. Then I had the experiment, made it sealed with those tightening foam things, and upside down and turned upside up. And there is a significant difference. And then I put the seal inside the box and waited only for 195 averages. And then 461 averages, I get the same result as I had here in the box. And removing the tape that made the box more airtight made no difference. And then I have changed the tuning, so I have turned it in 5 turns to position 12. And then I had before 112.87. And now, with the difference, with the stiffer box, I have 113.66. Well, the second decimal is not significant, I guess. And here is the result with the position 7 turns. And it's the same as I had inside the box and sealed inside the box. So it's differences in the second decimal, essentially. The difference from here, 11.9 or 11.8 to 110, that is 1.8 decibels. With more capacitance, the difference is smaller, from 112.9 to 113.7. And I think the reason why the stiffer box makes a smaller difference with more capacitance is that the sensitivity, frequency versus capacitance, is greater when the capacitance is small. That is obvious from this study. These points differ by 5 turns, from here to here to here. And the x-axis is frequency. So the curve looks like this, something. That here, at the minimum capacitance, the derivative is significantly steeper. And at maximum capacitance, This is also 5 turns from here to here. So when there is infrasound problems, a lower frequency works better. The best result at 12 turns on the capacitor is with a 50 ohm load in the feedback, and that is to reduce the level from 20 to 17 roughly, and it gives an improvement of nearly 1 decibel. While doing all the previous measurements, I have had the emitter resistor 340 ohms and the base resistors 82 ohms and the collector resistors 100 ohms. And I am changing these values to look whether something makes an improvement. And first I increase the emitter resistor to reduce the current here in order to reduce the feedback power. So first I change it from 340 to 460. This was good. I have now 114.17 after 1052 averages. As it turns out, there seems to be an optimum for the emitter resistor. At 460 ohms, 114.17, and then it goes down a little. Maybe not really statistically significant, but the signal level goes down, so I go for this value. And then I tried to change the base resistors, increasing significantly. That made a small difference in the wrong direction. So I think I keep these values. And then I have removed the load resistor, and that increased the signal level significantly and also improved the noise performance just a little. The load resistor on the primary of the transformer, the output transformer, I have removed it. It was forgotten in the previous schematic diagram, but it was there all the time. This is the final design. These values, 82 ohms, 470 and 100 for the limiting amplifier. This capacitor as well as this capacitor are tuned for maximum output. And I added a buffer and amplitude amplifier to boost the power to plus 17 dBm, and these are BF240 transistors. The limiting amplifier uses BFR91A. It gives a slightly lower phase noise than the BF240 in this configuration. In the first stage, this capacitor is tuned for minimum voltage in this point, while this capacitor is tuned for minimum noise at wide separations, and that can be done when there is no oscillations, that is, with the feedback disconnected from here. The oscillator is now back in the 2-channel receiver as channel number 1 oscillator. And this is the test object for the moment, the Wenzel 501 25420 oscillator. And here are the specifications from Wenzel. After 11 hours and 58 minutes, the average noise in the region where I usually measure it is 110.8. So it is about 4 decibels more noisy than the oscillator I have in channel 1. And in the measurement here, you can see that channel 1 and channel 2 have the same noise at 0.2 Hertz. And channel 2 is a little better at 1 Hertz offset, while at 0.1 Hertz offset there is a significant difference in that channel 1 is much better, 2, 4, 6, 7 decibels better than channel 2. And I guess this is because of infrasound in the channel 2 oscillator. The frequency offset is 40 Hertz. So here I have interference, and also at twice that frequency, this peak here. At about 20 Hertz, the channel 1 oscillator is 2 decibels worse than the channel 2. And it's clear that channel 2 is better at higher offsets. And that is valid also here. And that's the limit for this setup, 250 Hertz. Now, the difference is only 2 decibels. So I will not try to do anything about it. Channel 2 uses FETs. Channel 1 uses bipolars. Here is the result. I have drawn 3 straight lines. Frequency to power minus 1. That's 1 over f, or flicker noise. I have only 2 points that fit the line, but I know the slope of it. And then there is f minus 2, questionable, but I think it is about like this. And then f2 power minus 3. This straight line fits very well in this range, but here it bends upwards. At 0.2 Hertz, the difference is only 1 decibel, but at 1.5 Hertz, it is 3 decibels. I don't know the reason for this, but I suspect it is the instability of the power supply. I have an RC filter with about 10 ohms and about 1 farad capacitance, but the Wenzel oscillator is rather sensitive to variations in the supply voltage. These circles are the manufacturer specifications for typical performance. The f-2 line here is because -1 and -3 cross here, exactly where I have a measurement point, and it is more than 3 decibels above the crossing point. The sum of 2 equal should be 3 decibels, but it is a bit higher, and that's why I think the f-2 line comes here. So there are 3 lines that add together to get 4 decibels, roughly. I'm not sure, but I think so. That also explains why the curve bends a bit here. That's too early to be caused by the flicker noise.